So, in this video we're going to be looking at annuities, but in terms of present values. So, in the last one we did future values, but in this one we're going to be looking at present values, which means what do we need now, or how much we need to invest now, or mainly invest. So let's look at say something that is 8.3% per annum compounded annually. The question is, how much do I need to invest today to provide $500 per year for the next 10 years? That is the question at hand. So, let's start looking at how we could provide this so we don't have to do any extra calculations here. Compounded annually. So my interest rate is per year. I got I equals 0.083 and equals 10. So you can just pull up the A is equal to, just say PV, present value, times 1 plus I to the power of n. So present value is equal to A over 1 plus I to the power of n. So let's look at this. Say, if you look at the end of the first year, say PV is equal to $500 over 1.083 to the power of 1. That is PV1 end of first year. And then PV2's 500 over 1.083 to the power of 2. And if you continue that pattern, PV10 will be 500 over 1.083 to the power of 10. The reason why it's still 500 is because I want 500 per year. That's our target. So, if you look at the way I went about this, then you can see that I'm basically gearing up to add all these together, which again gives me my geometric series. So, let's just skip right into the good stuff and just use our geometric series. I was going to kind of like sneak my way into the geometric series, but I guess you saw right through that. So, I got, well, what do I got? In terms of my interest rate here that I'm using in my series, my series isn't really growing. So, unlike before, where I had the interest rate being multiplied by my amount or my present value. My interest rate is actually being divided by my interest rate, so that'll give me, so if I was to write PV1 out, it would actually be 500 times 1.083 negative 1. And then the next term would be 500 1.08 negative 2 negative 3 and so forth. So my geometric value is not actually going to be a full positive amount, so my first value is this one. So that's my A value, which is 500 times 1.08 3 to the negative 1. And then I have my R, my interest rate, which is this. To the power of n, which is 10 years, minus 1. All that divided by 1.083 negative 1 minus 1. A little bit more complicated than I like it to be, but let's punch that into a calculator and you get 3310.11. So I would need to invest a sum of $3,300 and, well, 3310.11. I would need to invest that now to provide a payment of $500 every year for the next 10 years. Well, that's interesting. Let's try looking at another example. Something a little bit more lavish. Let's see. Let's look at the exact opposite of an investment. Let's say a loan. Let's look at a loan from a bank. Let's say the loan was for $200,000. $200,000 loan. And let's say the bank charges 6.6% per annum. Compounded monthly. And let's say we're gonna take 20 years to pay this loan off. So let's say I want to take this information and find out how much I'll be paying monthly. So let's start off with the interest rate compounding monthly. So 6.6 over 12 should give me 0.0055, and my end value 20 times 12, that should give me 240. So my present value value annuity geometric series. Let's just write that out first, and I'll start plugging them in. So, now that I have all this information calculated, I have my N and my I. I'm going to start substituting. Oh, I don't think I explained this formula. This formula, there's a long derivation for it, but this is the formula for present value of an annuity. So let's start plugging in. Well, like R is the letter R represents the monthly payments I'm going to have to do. N is the number of payments, the number of payments, I being the interest rate, and V being the present value of the loan, in our case here. So if you were to write this out, we have R, which we're trying to find out. And then in here we have 1 minus 1 plus 0.0055 to the power of negative 240 over 0.0055. And this will all equal, we have 200k equals R times 133.072. And when you divide both sides by 133, you actually get R is equal to 1502.94. That will be the monthly payment to pay this off. And that is a hefty loan because the monthly compounding, that's what's really screwing this person up. This person being me in this completely imaginary case, but yeah. That is all for this video on present values and annuities. I might actually do a video on deriving these formulas for present value and future value annuities, and even compounding interest. I feel like that's a really nice and confusing video to confuse people with. So that is all for this video, and I shall see you